Hey there, camels. Today I want to I want to start working toward, I think I'll get there, show how exactly all of these locals can really help you make your programs run faster. That's actually, I talked in the first video about how locals prevent things from escaping regions, and that's very true. But the reason that Jane Street is interested in all of these locals is to actually make programs faster, and that's by controlling how we do allocation a little bit. So I kind of want to demonstrate how that works by showing that by using locals, we can reduce the amount of allocation a program needs to use. So just as sort of a quick reminder, you can find link in the description below about how to get the compiler that I'm working on. The compiler that I have here is Jane Street's branch of the compiler. These are working on experimental features that we are expecting to upstream and put in the regular OCaml after consultation and working with the community. Let's try to sort of work up an example here. So I'm going to have a very basic little program here that's just going to say do it. And so we have a do it function. And this do it function is going to create a bunch of lists and then just see how many members, they're going to be int lists, and we're going to see how many elements in the int lists are divisible by 5. Not maybe the most interesting thing, but something that we can write. So so here we're going to make let list equal, well, hold on. I want to do this in a loop. So we're going to say for I is 1 to 10,000, just so we get a bunch of, we can sort of have something to measure. It needs to be kind of a biggish number here. And then at each level, we're going to say let list equal, well now, first we need to generate a random length. So we're going to create a random length, let's just say under 10. And then we're going to create a list of that length. We're going to say list.init of that length, and then each element of the list is going to be a random number, say less than 100. And then we're going to want to count how many elements in each list are divisible by 5. So let's see. So we need to have a place to store that count. So we're going to have a little variable here. So let count equals ref 0. And of course I could do this using recursion, and that would work fine. And maybe we'll transform it to that later if we have time. I don't think it'll be quite worth it. And so then here I'm just going to say list.iter, and what's the thing that I want to iterate? Well, for each element in the list, if n mod 5 is 0, then count is incremented. That looks good, and then I want to iter over the list, and I think that's good. And then let's just print out what that final thing is. So we're going to say format.printf count. Okay, so there's my little program. Does it work? That's a good question. Let's see. Probably doesn't. Oops, especially if I misspell the file name. Let's see. So we do that, and then that's going to produce this a.out thing. Oh, and it does work. And if I run it again, it keeps. Oh, that's because I didn't initialize the random thing. That's fine. I actually don't really want to initialize the random thing because I want it to be consistent. So let's just say random.init 1, 2, 3, 4, 5, and that way I know it's just going to be consistent. And let me compile that again. Okay, now we get a different number, but I'm sure it's going to be quite consistent. Okay, so we have this program. Now I want to see how much does this allocate, right? It should allocate a fair amount because each of the 10,000 iterations is creating this list. And then we're just kind of iterating through it. Maybe a very fancy optimizer could get rid of the list, but that's not what we want to rely on. This is meant to simulate some amount of work. And so we want to know how much is this actually allocating. Well, let's look at the OCaml manual. So here we have the OCaml manual, and this is, by the way, very good reading. I definitely highly recommend it. If you go down here to chapter 15, the runtime system, then we can go through all of this, and then eventually you can find your way to OCaml run param. And in caml run param, there's this setting v, and if you set it to this 10th bit here, then it outputs GC statistics at program exit. So over here, let's do that. And so that means I can say OCaml run param equals v equals 1024, and then I can run my a.out. And then now, along with the actual, whoops, I've scrolled too far. Along with the actual output up here, it says how many allocated words. So it's allocating 204,000 words here. And let's just make sure that that's not some kind of baseline, that it should actually vary in the number of iterations. So if I change my program like that, and then now I recompile and run, then now we have many, many fewer allocated words. That's good. We want this number to have a direct influence on that number. We could measure it and show that it's linear. It's all fine. Everything is working well here. Okay, the beginning of the video started talking about locals. So far, this isn't all that interesting. Maybe it's a little interesting because now we can now easily see how much allocation our program is doing. So that's kind of fun. But we would like this number to be smaller because actually when I analyze my program here, I realize that this doIt function, well, actually every iteration of this loop here, by the end of the iteration of that loop, I'm done with that list. I don't need to use mark and sweep garbage collection. What I really should be able to do is just say, something like, if I were writing in C, there'd be something like free list over here. I'm not writing in C, so I'm not going to write that. But at the end of each iteration, I know I'm done with the list. And that's exactly the kind of control that locals gives us, right? So when we go back to how I've been describing this, locals allow you to or the locals feature allows you to say that a certain value doesn't escape. And so that's really what I want to say about this list, is that this list value never escapes this little region in here. So if you've been following along, you've seen I have every function defines a region and that a local value does not escape its region. Well, here I'm talking about a loop. That's actually another place where a region comes in. So every function and every loop body defines a region. So there's not, we don't write as many loops in OCaml as we do in other languages, of course. But here we do have a loop body, and that does define a region. So that means that if something doesn't escape, then we should be able to label it as local. So let's try that. So I can write local here. And then now if I try to compile, this value escapes its region. And that's because I'm sending it to list.iter. And so the problem is, as I've said before, the standard library has not yet been enhanced to know about locals, really. And so that means that we have to write our own functions. But actually, I kind of wanted to use that as a good excuse in this video to show how we write functions that operate over locals. So let's write the iter function. So we're going to write an iter function that takes some f and, well, I can just say equals function at this point, can't I? Because if I have nothing in my list, then I do nothing. If I have x followed by x's, then of course I'm just going to iterate the function on x and then iter f x's. Okay, is that enough? And then I have to use the iter function. And so let me recompile and rerun. And nope, we still have lots and lots of allocations. So one thing though that we should be careful of is that I've been compiling with OCaml C, which is the unoptimized bytecode compiler. It's a topic maybe for another day, but OCaml has sort of two different modes that it can run. It can run in sort of a cross-platform lower performance mode or a single platform higher performance mode. And we want that second one for these experiments. So I'm going to switch, instead of using OCaml C, to OCaml opt.opt, which operates the same way, but just compile something that will only run on my machine here. So already we get lower words, but this is not the sort of the zero. We want something quite close to zero here, is what we're going for. So this is clearly not doing the trick. And that's because this iter here, well, how do I know whether this is local or not? The best way of being sure, because OCaml will infer locality when it can, but I don't want to just rely on that. I want to make sure that this is doing what I think it's doing. So let me give the full type for iter here. So it's going to be parameterized over some type variable a, and let's see, it takes some function from a to unit, and then it takes a list of a's, and then it returns unit. Okay, So I've written that. Oh, this escapes its region. Oh, so I guess previously, before I gave a type to iter, it was inferring that iter was local because I had the word local here. And if it weren't inferring locality, then I would have gotten an error. Let's replay that in slow motion. So if I get rid of this type annotation, and then run the compiler, everything is okay with this local annotation. So that means that the compiler is inferring that this iter indeed doesn't preserve the list anywhere. Once I've given the type annotation, well, now we don't say the type annotation does not have the word local here. And so the type says, well, maybe this escapes. We don't know. It doesn't say anything about whether or not it escapes. So we're going to conservatively assume that the list does escape. And that means that when I try to compile, I get an error. So we can fix that by writing local there. And I still think we'll have a problem. Yeah. So now this is saying that this is a local list. And that means that not only can the list not escape, but nothing in the list can escape. And here I've called f on an element of the list, x. And so now we have a problem because here we see, well, this f here that comes in, maybe that saves the value somewhere. So I also have to label that as local. And then that now it works again. So now we have an iter function that works on locals. Again, I didn't need to write that type annotation, but now I can be more confident that that's really working. And yet, when we, whoops, what's going on down here? Oh, I just haven't hit the button. There we go. And yet when we run it, we still have a lot of allocations. And that's because this list, even though it's labeled as local, it wasn't born that way. And that's because it's built using list.init. And so list.init, that allocates something that might escape, right? The return type of this is just a list. It's not one of these local lists. So not only do I need to rewrite iter, I need to rewrite list.init. This kind of bug that we're seeing right here can be a little bit hard to diagnose because it looks like this should be local. But as we remember from previous videos, global is a submode of local. So even if this list.init returns me a global list, I can sort in this local thing. What I'm really saying to the type system here is, well, that list that's coming in, well, maybe that can escape. But I'm now going to make this local variable list which cannot escape. And of course, losing the ability to escape, that's fine. There's nothing that violates our type system guarantees by losing the ability to escape. But here I want more than that. I want to know that when it was born, when it was allocated in a way that couldn't escape. And that's not something list.init can do. So that means I have to write my own init function. Okay, so I'm gonna write an init function here. So init is gonna take some length and some function f, and let's see, what is it going to do? Well, I'm gonna make a little loop to build this up. So we're gonna do that using a recursive function with an accumulator here. So let's say we're gonna have let rec loop, and then we're gonna have n, the index of the element that we want, and some accumulator. Let's see. And in here, we're going to say if n is less than 0, then we're done. We're just going to return the accumulator. Else, we're going to call f. Let's see. So if I say n is less than 0, so that means the last one, f, or n will be 0. So I want to call fn and cons that onto the accumulator, but I'm going to recur with that. So I'm going to call loop n minus 1 with that. That looks about right to me. And then, of course, we need to, and then the initial call to loop is going to be loop with, we're going to start with a length minus 1, and an accumulator that's empty. That looks right to me. Let's try that. Wow, it compiles. Okay, does it run? And it should produce the same value. Let's see. Yes, 8987. So this. I've written a function, but I haven't called it. That's not very interesting of me. Let's try that again. It still compiles, thankfully, and then I run it, and 89, 87. So this actually now allocates a little bit more. It turns out that the built-in list.init might be more efficient in some way. That's fine. We're not going to really try to optimize. But the important thing is that this init actually is doing the right thing, and we can see that by it producing the right value here. Maybe the built-in one operates in the different direction than this one does. Doesn't matter. Okay. So is that solving my problem? Well, clearly not, because I'm still clearly allocating lots and lots of memory. And so I'm going to go here, I'm going to repeat the exercise, and then let's write out the full type of init here. So it's going to take the length, it's going to take some function, which takes an int and then produces a local a, and then this produces a local a list. And let's see about that. Oops. This value escapes its region. Let's see, where does that value escape its region? So here, this call to fn is saying that escapes its region. So let's just try to analyze that a sec. So this f has this return type here. So it's producing a local thing that can't escape. And it's being used as an argument to loop. So somehow loop must be expecting something that's not local. Well, of course it should be local, so let's just label that as local, and now we can maybe get a better error message. Oh, this value still escapes its region. Why is that value escaping its region? So maybe this has to do with the fact that we are here in the tail position. So, as we discovered earlier, return positions, also called tail positions, are treated specially. And we will probably in the next video get to explain why that is. But by putting a non-tail annotation here, well, that's kind of bad because I do want this to be a tail call. So I think we'll come back to that. But let's see, does that fix the problem? It does fix the problem. Now it says that this whole thing escapes its region. And the reason it's saying that is that actually what I want to say here is that this loop here needs to return itself. This needs to return something local. So if I annotate this as returning a local list as opposed to something else, then, that just says syntax error. Why does that say syntax error? I expected that to be able to work. Maybe we don't allow local underscore there? That's a bit silly. We really should. Instead, let me write out the full type of loop. So it's going to be int to a local alpha list to a local alpha list. Okay. Oh, and now what do I have? Now I have syntax error. Why is that a syntax? Oh, because I've done this. These parentheses are no good. Because as I've said in a previous video, that's kind of weird that the parentheses are no good. As I said in a previous video, this local underscore is really something that's talking about that arrow and not about the list. So by putting the parentheses, it sort of prevented the local underscore from getting to the arrow. Okay. So this local value escapes its region, cannot return local value without an explicit local annotation. So that error message is a little bit outdated because we should really be using exclave rather than local. But the idea is that every function defines a region. But actually, this thing that I'm returning, I want that to escape. Or really, rather, I want that not to be allocated in the function's region. And so I'm going to say exclave here, and then I can get rid of this non-tail thing. And that might move us further. That does move us further. That moves us down here, and it's saying that this escapes its region. And that does make sense because this loop is producing a local value, and yet I'm trying to return it out of a function. And so once again, I need to say exclave, saying that down here, I don't want this to allocate in the function's region. I want this to allocate sort of outside. I want the region to end early. And so now this works. And now, do we get the good allocation behavior? So now we run it. And now, let's see, we have 90 some odd thousand allocations, but I think that's a lot less than we did before. So let's just change, instead of init down here, if I change this to list.init and compile and run, now we have 177,000, right? So using our local one, cut our allocations by 2. I'm surprised it's only cutting it by 2. It should cut it by a lot more than that, I think. Maybe random.int does a lot of allocation. I think I know. Okay, so this will be a cute thing, and then we'll wrap up for today. So both iter and init take functions. Well, when I make the function here, so what OCaml can do is it can analyze this little function and see that this doesn't capture anything from the environment. And so when it sees this, it will actually not allocate anything. It says that this function, it's as if it's defined out here. And so that doesn't allocate anything. This function, on the other hand, that does capture something from the environment. It refers to count. And so we can't put it up there. Maybe it does something clever and just sort of defines it once. I'm not sure. But to make sure that that's not doing its own allocation, I can take my function arguments and label them as local. And so if I do that with both of these, then let's see what happens. Now if I compile, oops. Now, the value f is local, so cannot be used inside a closure that might escape. So what's happening here is that this loop here, I've referred to f. This f is a local thing, but loop itself is not local. So I need to make loop local, and then that, again, I shouldn't really have to do that. All of this should be inferred. But then loop is local, and so it cannot be used inside of an exclave. So what's going on here? I said that loop doesn't escape its region, and yet I've used loop here outside of the region, so that's no good. So one way to fix that is to move that exclave up here so that the loop itself is outside. And then now, does that work? Yes, that does work. And then now when I run my program, oh, that didn't really reduce allocations. I expected that to reduce allocations a lot. Oh, I see what's going on. I'm calling the wrong init function. That's very silly of me. Okay, so if I delete that, then hopefully now if I compile and run, now we have very little allocation. So there's some stuff going on, probably some stuff from printing. But what this is really showing is that by constraining everything to be local and programming somewhat carefully, we need these extra exclaves, is that we're creating an init function that only allocates locally. We say right when everything is born that it's not going to escape. And that means that when the region ends, right here at the end of the loop, we can deallocate all of this memory. And so that means that here, I mean, this what it's saying here in the output, allocated words, is a small bit of a lie, right? Because it's still allocating the words. It's just not using automatic garbage collection to get rid of them at the end. It's the fact that we've reached the end of the region to get rid of it. And that means that we can do a lot less work on the garbage collector, which then can improve the latency of our programs. Next video is going to talk a little bit more about how this works and exactly where the memory is going. If you're interested, you can find a link to the code that we're looking at here, which is going to be posted on GitHub, and the link will be in the description. Thanks very much for watching. Hope this has been fun. Bye.